Hello, welcome again to our design of reinforced concrete beam to BS8110. I'm David Okot. I request you to subscribe, like, and share my YouTube channel. The question reads, show an elevation and a section through a reinforced concrete beam. The beam carry dead and imposed load of 20 and 18 kilonewton per meter respectively, assuming FCU 30 Newton per millimeter squared, FY 460 Newton per millimeter square, FYV 250, and exposure condition is mild. Design the beam. Take unit weight of concrete as 24. Use the information in table. There are tables provided. Then assume any other relevant information. Now, each mathematical question, a mathematical problem, the first step is for you to obtain the quantities given in the question statement. For example, we have a dead load of 20 kilonewton per meter and imposed load of 18, strength of concrete of 30, strength of main steel of 460, strength of shear reinforcement of 250, unit weight of concrete, that is gamma C 24, exposure condition is mild. Now from the table we know that if it is mild and then the strength of concrete is 30, nominal cover is 25, maybe you can choose and add 10, that 10 millimeter is the deviation in cover. You can choose and have a total of 35 millimeter or just stick to 25 millimeter. Then span here it is 6,000, not 600 as shown, 6,000 millimeter. The breadth of the beam is 300 and the overall depth is 600 millimeter. Now we shall go straight to loading. Now remember loading, you have two types of loading. We have the dead load or dead weight, and then we have the imposed or live load. Now for this case of our beam, remember the dead load is not inclusive of self-weight of the beam. Now in that regard, it means we shall have to compute the self-weight of the beam. Now how do we compute self-weight of the beam? We basically take the unit weight of concrete, we multiply by the cross-section of the beam. Cross-section of the beam here, it means you do what? You multiply B times H. Width times overall depth is what we call the cross-sectional area of the beam. So in this case, we shall take 24. Remember, kilonewton per cubic meter. Now we change the value of width and overall depth into meter. We shall end up with 4.32 kilonewton per meter. Now total dead weight will be equivalent to the 20 which we are given, which is applied plus the self-weight of the beam, giving us 24.32 kilonewton per meter. Imposed or live load, QK, we were given as 18 kilonewton per meter. From there, we shall move to ultimate load. Ultimate load here, you have a choice. If you choose to use capital W, then you have to multiply the loads by the span to come up with a value of kilonewton. But some books will opt to use small letter W. In that case, you don't multiply the product or the sum with the span, meaning your value, the ultimate load, when it's small w, will end up with kilonewton per meter. For our case here, we are using capital W, in that now our ultimate load is 1.4 dead load plus 1.6 imposed load. Then you multiply by span. Now remember span here. Now we are dealing with kilonewton per meter, meaning span we shall use it in terms of meter, not millimeter. So we use 6. From there now we get our value of ultimate load as 77.08 kilonewton. Now we have design moment. Design moment here means what is coming from the applied loads, what is being applied on our beam. Now design moment here will be given by, now since we converted our W into a point load, into kilonewton, it is WL over 8. Now it is basically, this 377 is a point load acting at the mid span of our beam. So we use WL over 8, which is 282.816 kilonewton. kilonewton. Then from there, we move to, maybe we can compute what? Our effective depth. Now, how do we compute effective depth? Effective depth is equivalent to the overall depth minus cover minus diameter of the main reinforcement divided by 2, or half the diameter. Then we have the ultimate moment of resistance, MU. Now, ultimate here, it means what is the capacity of our beam? What can it carry? Which quantity or amount of moment can this beam carry without collapsing? That's what we call the ultimate moment of resistance. So it's normally given by 0.156 FCU, strength of concrete, times B times D squared. Now, remember we said for you to find effective depth, which is D, you have to take overall depth minus cover minus diameter over 2. Now, here it will mean I will come and assume diameter of main bar, but you must make a competent assumption. What do I mean by a competent assumption? You will go to the table of diameter of steel bar. You pick a value from there. For example, you cannot take a diameter of bar as 14 millimeter. Why? Because in our reinforcement table, we don't have a bar with 14 millimeter. We only have 8, 10, 12, 16, 20, 25, etc. Now you have to pick a value from the customary section, customary diameters given in the table of reinforcement. So for this case, I assume the bar is 20 millimeter in terms in diameter, which meant that our H was the overall depth from the cross section was 600 minus 35, the cover we computed due to exposure condition and cover deviation. Now will give us 555 millimeter, which means our ultimate moment of resistance will be 0.156 times 30, which is strength of concrete, times 300, which is B, times 555 square, which is D. Now, the reason we multiply by 10 power 6, if you compute that value before 10 power 6, it will give you Newton millimeter. It will be a moment, but in terms of Newton millimeter. But now, for you to change Newton to kilonewton, you divide by 1,000. To change millimeter to meter, you divide by 1,000. That is why we are multiplying by 10 power negative 6, negative 3 Newton to kilonewton, negative 3 millimeter to meter. Now, then you will come and say, now our value we are getting 432.467. Now, which is more than the design moment. Now, you have to say that since the ultimate moment of resistance is greater than the design moment, then no compression reinforcement is required. Compression reinforcement are those reinforcement steel bar which are placed in the compression zone. Remember, when you have a beam section, where is I can't see the pen, but when you have a rectangular beam section, remember the lower part is under tension and the upper part is under compression. But remember, there is no beam in practical life that has only bars in the bottom section. What do we do? If no requirement for the compression bars, now you provide there smaller bar which are acceptable by the design code, which shall be used as hanger bars. Hanger bars, their work is to ensure now the shear links, what we call links in layman language, they should be able to form a rectangle pattern. So we shall provide bars in the top zone or in the compression zone that we call the hanger bars. Now let's proceed. Main steel area, AS. Now we have to compute a coefficient K. Coefficient K is the design moment. Take note, design moment M divided by FCU BD square. Remember, FCU is the strength of concrete. Now the design moment was 282.816. But now remember here, this value of design moment is in kilonewton meter. But if we take FCU BD square, they are in Newton and millimeters. So for us to ensure the upper value is in the same unit with the lower value. We multiply the upper value by 10 power 6. So the value of our k, if you compute, you get 0.102. And then now we go to arm length, which is Z. Now from the code, the BS8110 code, we are being told that Z is equivalent to D into bracket 0.5 plus the square root of 0.25 minus K over 0.9. But this value should be either equal or less than 0.95 D. What does it mean? It means if you get a value of, assume Z is equivalent to 0.82 D, that is okay. You say Z is equivalent to 0.92 D. But if I compute what is in the bracket here and find it is 0.98, then that's not acceptable. I will rule out and say my Z is 0.95 D. So wherever the value in the bracket exceeds 0.95, then you rule out that your Z is equivalent to 0.95 D. So in this case here, the value, our value in bracket is 0. Our value in bracket is 0.87. Is 0.87. So this will mean that our Z will be equivalent to 0.87 D, where we substitute our D was 555, we get 482.85. Now, still area, we proceed and say is M, design moment divided by 0.95 FYZ. Fy is the strength of main reinforcement bar, or the strength of main steel. And remember, this 0.95 factor, it will depend with the version of BS code. Others will use 0.87, which is okay. Others will use 0.95. It will depend with the version that is being used. But basically, area of steel for our case, we shall use 0.95 Z. Now, remember, we are using design moment because the steel bus we are designing is to take care of the bending moment that is applied from the load. Now, this will give us, now the same case, we shall, this 10 power 6 is to change the values of design moment to Newton millimeter so that they are uniform with the rest, so that we end up with a value of a millimeter squared. Now, our calculated area is 1,340 millimeter squared, right? Now, remember, we made an assumption that the diameter of our main bar is 20 millimeter. Now, what do? You come to the table on the row of 20 millimeter. Now, move along that row until you see a value equal to 1340 millimeter square or slightly above 1340 millimeter square. That's why I told you when you are making an assumption of diameter of main bar, you must use this column bar diameter. You take any value here that is practical. But remember, in our country, Kenya, I think we cannot allow the use of main bar, which is less than 12 millimeters. So you need to adopt at least a bar diameter for a beam of 12 millimeter going upward. So what will happen, I will move along 20. Now, looking at that, you find that along 20, I have 1257 below 1340. Then I have 1571. Now, since 1571 is the value closer to that, and because I wanted to be consistent with the 20 millimeter, I will opt for 1571 millimeter squared. Although someone else will take, I know 1407, and then he will rule out that is 16, that is 716 diameter bar. But now at some point we also look at the practicality, because it might be difficult for someone implementing the project to have the 7 bars. Maybe concreting will be difficult. Yeah, so sometime I know we can maybe move and adopt like maybe 1473. Those are 25 millimeter diameter bar. Now it will depend when we arrive at this point. For our case of learning, let us stick to our 20 millimeter, giving us 1571. But in reality, sometimes it might not be the same. Why? Because of practicality issues. Now, assume you have to provide 8 bars. Now, how will you lay the 8 bars? How will you concrete? So, you have to be practical, especially if you are doing it for the field and implementation purposes. But for the purpose of learning, let us stick to our diameter of 20 and rule out that we shall take 5 bars, 20 millimeter in diameter as main reinforcement. So giving us an area of 1571. Now that's how we read from the table. Be careful, this area of group of reinforcement bars in millimeter squared. And then, now we shall move to shear reinforcement. Now for shear reinforcement, we know that the ultimate design load W, we obtain it as 377.088 kilo Newton. Now, then what you should know, our beam is symmetrically loaded and then it is simply supported. Now, in that particular manner, it means the value of reaction, end reaction are equivalent and which can be obtained by taking the total load divided by 2. Then ultimate shear force is same as the end reaction. So our ultimate shear force will be 188.544 kilonewton and design shear stress. Now remember, in hydraulic, we talk of force and pressure, but in structures, pressure we call it stress. That's why now here, the design shear stress is equivalent to the ultimate shear force divided by the area, which is the cross-sectional area of the beam, BD. Now we have to convert 188.544 kilonewton into Newton. That is why we multiply by 10 power 3. Then we had our B as 300 and we had our D as 555. Now we shall end up with 1.132 Newton per millimeter square. Then now this design shear stress, it means the applied load will make the beam undergo that stress. But now we go to design concrete shear stress, VC. Now this is the shear stress that beam can withstand without external support. Now how do we compute it? Now we have to compute a parameter which is 100 times area of steel divided by cross-section of the beam, which is BD. Now, the area we use here is the area provided, the area you read from the table, because that's the actual area that will be put into the RCC beam. So from our table, we had 1571. Remember, 100 is fixed. So it's just a constant, like a percentage. Then we know our B is 300 and our D is 555. Now we get a value of 0.944. Now look at the table on our right-hand side. Table 2, value of design concrete shear stress, Newton per millimeter square. Now, column 1 talks about 100 AS over BD, and then column 2 talks about effective depth D in millimeter. Now let's get back. One thing, now when we talk about column 1, our value of 100 AS over BD is 0.944, right? And then for column 2, our effective depth is 555 millimeter. Now looking at it, the effective depth value starts from 125 up to greater than 400. Now, our value being 555 millimeter, it is Now it lies in the column of equal or greater than 400. And then our 0.944 on the column of 100 AS over BD, it lies between 0.75 and 1. Now, in this case, you can opt to use interpolation. How? You will come and say at 0.75, move along that row. On the first column, 100 AS over BD, we have 0.75. It gives us a value of what? 0.57. Then the value of 1, now that is in the column of 100 AS over BD, 1 gives us a value of 0.63. Then now we shall come and ask ourselves, how do we compute for the value of 0.944? Now here it is easy. How? I will come and subtract. Now on the first column, from 0.75 to 1, I know they are 0.25 unit. I go to the second column for now not effective depth, for the value of design concrete shear stress. At 0.75, I have 0.57. At 1, I have 0.63. Now I will subtract. So when you subtract 0.63 minus 0.57, you get 0.06. So I will come here and say, if on 100 AS over BD, a 0.25 change corresponds to 0.06 change in the design concrete shear stress, what about, now I'll come and subtract 0.944 minus 0.75. Then now the value I get, I take that value, that is 0.944 minus 0.75, so is equivalent to 0.194. I divide by 0.25 that I got. Then you multiply by the change in shear, design concrete shear stress 0.06, which will give me 0.04. Now this value, now look at the trend. It means at 0.75, it is 0.57, and at 1.0 is 0.63. Now this tells you that it is an increasing trend. Now, if it's an increasing trend, I will come, the value I get, I add on 0.57. Some will subtract it from 0.63, still is the same. So that is why we arrived at approximately 0.656 Newton per millimeter square. But remember, this table value apply for a concrete strength of 25 Newton per millimeter squared. The tabulated values are strictly for 25 Newton per millimeter square. This is as per the British Design Code. Now, if I want to find the value, now our concrete strength for this question was 30 Newton per millimeter squared. You take FCU over 25 power a third times the value you obtained. So this will be equivalent to 30, which is our FCU, times 25 raised power third. I multiply by 0.617. I get 0.656. So that will be the value of our design concrete shear stress VC. Now let us now proceed. Now look at table 4, which talks about form area and spacing of links in beams. Now this is how we shall start. We shall come here and say, now let us look at our category. We know that our value of design concrete shear stress is 0.656 Newton per millimeter square, and the design shear stress is 1.132. This means that the design concrete shear stress is less than the design shear stress. Hence, the beam will need shear reinforcement to help it carry the excess shear stress. That's why we conclude and say, since VC is less than V, shear reinforcement is required. Now, let's go to table 4, which talks about form, area, and spacing of links in beams. Now, in table 4, we have 3 conditions. Now, condition 1 is where V is less than 0.5 VC, which is not our case. Now, in this case, they say no links required, but nominal practice provide nominal links in members of structural importance. Then, if it lies between VC and VC plus 0.4, you provide nominal or minimum link for whole length of beam, which is given by ASV greater or equal to 0.4 BSV over 0.95 FYV. Then if we have a case where the design shear stress is greater than VC plus 0.4, but less than the lesser of or the smaller of 0.8 square root of FCU or 5 Newton per millimeter square, you will design links according to AS is greater than or equal to BSV multiplied by V minus VC over 0.95 FYV. Now remember, the value of design shear stress should never exceed either 8 root strength of concrete or 5 Newton per millimeter square. Whichever is less of the two, the value of design shear stress should not exceed any of them. Now, for our case here, now that our value exceed condition 1 that says no links are required, we shall move to condition number 2, whereby condition number 2 means the design shear stress is more than concrete shear stress but less than. No, we shall take a case where the design shear stress lies between design concrete shear stress and design concrete shear stress plus 0.4. Now, in this case, we are given the formula. Now, remember this formula, which is ASV greater or equal to 0.4 BSV over 0.95 FYV. Now, we are going to we divide each side by SV so that now for the first part, as I told you, where V lies between VC and VC plus 0.4, as per the table, we shall take ASV over SV is greater or equal to 0.4 B. Remember, this is breadth divided by 0.95. Now, FYV means the strength of shear reinforcement steel. Strength of shear reinforcement steel. Now, which is 0.4 being 300. Then our 0.95 is a constant, like we said, it depends with the addition of the BS8110. Now, FYV, strength of shear reinforcement, we were given as 250 Newton per millimeter squared. Now, we get a value of 0.505. Now, what do you do with this value? You come to this table here. Now, look at this table, table 5, values of ASV over SV, VC, diameter, and spacing of links. Now, we will come and look at that. Now, remember our value is what? 0.505. Now, when you go to this table, table 5, which talks about diameter of links as first row, then spacing of links as second row. Now, I will try to locate a value of 0.505. Now, for our case here, we opted for 0.523, which means you provide 10 millimeter diameter links spaced at 300 center to center. So R10, or we can call it Y10 or H10, at 300 millimeter center to center. How do we obtain it? Now you move along diameter, and then you also move along what? Spacing. Now we have 0.523. Now that intersection of 10 millimeter diameter and 300 center to center gives us the diameter and spacing of links. Then, but the code requires that the maximum spacing of links should be a maximum of 0.7 effective depth D. So if I compute 0.75 times effective depth, which is 555, I get a value of 416, meaning 416 is greater, or in simple term, the 300 recommended spacing is less than 0.75 D. Now here we want to determine, because remember in our beam we have two cases, a case whereby V lies between VC and VC plus 0.4, and another component lies between VC plus 0.4 to the maximum, which is 5 Newton per meter square, or 0.8 root FCU. Now for that, now how do we compute where the first case will be? Now we shall come, our beam is 6 meter, we divide it into 2, 3 meter, 3 meter, and then, now remember the shear force is highest at the ends, which is what? Our shear force, but now we converted to shear stress, which was 1.132, 1.132. Now they are 3 meter, both of them are 3 meter from the midspan, because the beam is a total of 6 meter. But now we want to determine where the reinforcement will end, because if we take VC plus 0.6, we get something close to 1.056 Newton per millimeter squared. Now we shall apply law of similarity and say, now we have two similar triangles. Now a triangle which run from the center of the beam to the end of the beam, and a triangle that runs from the center of the beam to where we have a shear stress of 1.056. In simple terms, I mean, if I take, now a smaller triangle has a measure x, I divide by this height here, 1.056, is the same as I take 3, which is the measure of the larger triangle, divided by 1.132, which is another measure of the larger triangle. So this gives me 2.8. So this tells me that this 10 millimeter at 300 center to center link should be placed a distance of 2.8 meter on either sides of midspan. That's why I conclude and say, hence provide R10 at 300 2.8 meter either side of midspan for this value, because this is a case where V lies between VC and VC plus 0.4. Now let's look at the second case where now V design shear stress is greater than VC plus 0.4. We have been given a formula as above. Look at table 4. We have been told in that case we take AS over ASV B into V minus VC over 0.95 FVY. So this is how we proceed. We just substitute. B is 300, V is 1.132, VC was 0.56. We have 0.95 times FVY is 250. Now we get a value of 601. The same case, ASV, remember table 5 is just value of ASV over SV. So this 0.601, maybe because I wanted to have similar diameter, of shear reinforcement bar, I will still move along 10. So if I move along 10, you find I have a value of 0.628 because the value should be either equal or slightly above. Now that I have 601, I will opt for 0.628. Now 0.628, look at that table. It tells you that you need a 10 millimeter diameter bar spaced at 250 millimeter center to center. Now then from the table, you provide R10 or Y10 or D10 depending on the specification given. I used R here because for steel of 250, it has a low or a medium strength. Now hence provide R10 at 200, 250 center to center, 0.2 meter in from post support. Why? Because this 2.8 meter, it is from the center on either sides of mid-span. So the total is 3 meter. Already 2.8 meter is covered. So the remaining is 0.2 meter. So the shear reinforcement at 250 center to center will only be included in the 0.2 distance in from both supports. Then now we go to deflection check. Now deflection check, we start with what? We start with the effective span. Remember effective span, we have two formula. We either use center to center distance. Our case, we are given center to center distance, like from the middle of the supporting wall to the middle of the second supporting wall. So in that case, it's center to center distance, or if not, we take if a clear span. Clear span means distance, internal distance from the support, then you add the effective depth. Now, whichever is less is what you use as the effective span. In most cases, we take effective span as center to center distance, center of the support, center of the wall, center of the column supporting the beam. Actual span over D, span is 6,000, D is 555, is 20, is 10.81. Now we have the basic ratio. Now look at table 6, basic span depth ratio for rectangular section. Now support condition and then span effective depth. Now for our case, it's a simply supported beam, so basic ratio is 20. Then now we want to look at modification factor. Now modification factor, first we can compute M over BD square. Remember, M is the design moment. So design moment over BD square, we multiply design moment by 10 power 6 to convert it to compatible unit. We get 3.06. Then we have what we call the service stress. Fs is normally given by 5/8 times strength of main reinforcement, you multiply by area required. Area required is what you calculated, divided by area provided. Area provided is the area you read from the table, you obtain from the table. So if we substitute, and 5/8 are constants, if we substitute, we get 245 Newton per millimeter square. Then modification factor is normally given by, you can see when you have been given the formula in table 3, equation 4. So you have been given the formula is 0.55 plus 477 is fixed minus service stress over 120, open bracket 0.9 plus M over BD square. And this value should be a maximum of 2. Should be a maximum of 2. Even if you get 3, you only use as 2. So it can never go beyond 2. So if we substitute, we get it is 1.04, which is less than 2 is okay. Now, which means permissible or allowable span of effective depth ratio is, we take modification factor 1.04 times basic ratio I said it is what? 20 because simply supported beam. Then it will give us about what? 20.08. Now, since our actual span of effective depth is less than the permissible or allowable, then we say our beam is okay in regard to deflection. Now, to sketch reinforcement detail, this is how we do. Now, the first one on the left-hand side, it is along the cross-section of the beam. We cut the cross-sectional area of the beam. Now, here you can see 5H20 bars in the bottom. In the bottom, we call them tension bar. And because we didn't require a compression bar, we just provided two diameter 12 bar to act as hanger bar over which now the 10 diameter links are being supported. Because you see, in practical aspect, you cannot have a beam with bars at the bottom only. You must provide hanger bar where you will tie your link. Others call them links, others shear reinforcement, others call them stirrups. It depends, provided the main purpose is to help the beam to resist the shear stress. And then now the other end here, now when you look at the second picture where we have 2R10 at 250 center to center, and then we have 19R10 at 300 center to center. Now, this is the bottom bar here is the diameter 20 bar, and then what we have at the top here is diameter 12, what we call hanger bar, and then whatever is crossing the vertical ones, those are like they're showing the diameter 10 links will span from there to there. There will be 19 of them spaced at 300 center to center. Then we shall have two of them diameter 10 spaced at 250 center to center. You see, if you want, maybe if you want this house to be, or this beam to be constructed, this is the final product you give the whoever is implementing. So for him, he'll be able to interpret what you meant by this. So reinforcement detailing is very important because it informs whoever is implementing the project on how to place the bars, at which distance, and other detail. I hope you've enjoyed this video, and thank you for watching. Thank you for supporting me. I'm looking forward to give you more entertainment, especially in structure. I'm working on Eurocode, and because Kenya, we are shifting from the British to Eurocode in terms of reinforced concrete, steel, and timber design. So I hope you'll be enjoying. Keep in touch. Ask any question, I'll be willing to answer. Thank you. Have a nice time.